Good morning. My name is Peter Bostock, and I'm with VDE Americas. We provide owner's engineering and independent engineering services to investors and OEMs here in North America. We're part of VDE, I would say a blend between UL and IEEE, offering certification and other services worldwide with headquarters in Germany. I'm here to talk about hail and tornado risk modeling, and given the 15 minutes maximum, I will focus on hail, but I'm happy to address tornadoes as people have interest in the Q&A session later on this morning. So, components of hail risk. Basically, there are three components: the weather, the system exposed to the risk, and the predicted financial impact. Obviously, weather depends upon the location, and we are interested to know the probability of occurrence of potentially damaging, naturally occurring hail at that location. We also need to know the specific module resilience to hail impact, be it crystalline silicon, 2mm glass bifacial, traditional 3.2mm glass and polymer backsheet, or thin film glass, etc. Also, we need to know what operational mitigating practices are possible, for example through safe stow mode of the modules on the tracker. Finally, the financial impact depends upon all the above, but I'll get to that in a bit more detail later on in this presentation. I believe that there are gaps in our industry knowledge that need to be filled, but I believe we can start by making more educated guesses. So there are two publicly available databases of which we are aware, and both of these databases should be approached with some care. The first is NOAA's SPC spotter database, and the second is NOAA's NEXRAD Doppler radar database, and both have pluses and minuses. In conjunction with Professor Allen of CMU, VDE has developed a tool to blend these two resources to provide return intervals for different sizes of naturally occurring hail across the continental US. The databases variously go back to 2000, and even in the case of the spotter database to the mid-50s. We can provide mean and PDFs of sizes of naturally occurring hail and can provide values across different geographies, more local and more distant, both mean values and probability distribution function values. We can give you hail event history as reported, for example, by radar within an arbitrary radius, for example 20 kilometers from the plant, going back to the year 2000. So if you want to, you can see what radar reports in the last 20 years, and you can get from that some idea of what might happen in the next 20 years. In this slide, we're saying it's important to recognize that a hail event is not a uniform field of similarly sized hailstones. Rather, it's a spatial and temporal distribution through the event. Spotter data, as reported by the person on the ground, gives you the maximum size observed, and radar can give you a more detailed PDF with different p-values of size, but damage threshold is driven by the maximum size during the event. Radar, as we understand, needs calibration of the reported size, especially above 2 inches or so. And this calibration between the radar data and the spotter data can depend upon the particular radar station reporting and the range from that station, etc. So this slide is showing return intervals for various locations in Texas. And what we mean by return interval is, what do we expect on average to be the time interval between occurrences of naturally occurring hail, with the same size. And it shows that even within Texas is a big state, right? Even within Texas, there's a significant variation in that return interval as a function of hail size as we go away from the mountains of western Texas to the more moist eastern part of Texas. The return intervals of Texas are also compared with a typical return interval for a plant located in the southeastern part of the country. This slide is to say that, as we all know, naturally occurring hail is quite different from freezer ice balls. Naturally occurring hail varies in shape, but is more like an oblate spheroid of lower density, so it's lighter, and it falls more slowly than freezer ice balls of the same diameter. Its mechanical properties are quite different and also can vary considerably. There is quite a bit of literature around on those differences. Other industries have spent decades studying this topic. See, for example, the work of IBHS, the Insurance Institute for Building and Home Safety. That work is paid for by the insurance industry itself. And it appears to me that they've not spent much time looking at PV modules, spending most of their time on topics closer to the billion-dollar insurance losses, which turn to be on such things as residential roof shingles. Following the literature, we can plot the kinetic energy of naturally occurring hail and compare that to the kinetic energy of freezer ice balls of the same diameter. That is, granted the lower kinetic energy of naturally occurring hail, we can determine the diameter of freezer ice ball that has the same kinetic energy as naturally occurring hail, in this case by drawing a horizontal yellow line on the graph from the blue dashed line to see where it intersects with the solid red line for the kinetic energy of freezer ice balls. Of course, as shown by the work of RETC and others, a tilted module sees a much lower normal impact energy as the blow becomes more glancing, as shown by the dashed green line. In this case, 4-inch naturally occurring hail striking a module tilted at 50 degrees has the same normal kinetic energy of impact as a 2.5-inch freezer ice ball striking a module normally, for example, as in IEC 61215. Need to provide a couple of caveats on these equivalencies. The full impact physics should be included, and that full impact physics should include the mechanical properties such as mushiness of the naturally occurring hail and what happens with the fragmentation energy, etc. Also, I would point out that this analysis thus far does not include wind effect, so watch this space. This slide shows that if we can derive equivalent sizes for naturally occurring hail and freezer ice balls, we can plot equivalent return intervals for freezer ice balls. That is, the return interval in years for which we would expect there to be corresponding natural hail of the same impact energy. We can do this for both horizontal and tilted modules. We think this shows very clearly that both module resilience and operational mitigation are of the utmost importance if we wish to minimize risk. Operational mitigation means tilting the modules appropriately ahead of an approaching event. Operational mitigation means that in a hail-prone region in particular, one should consider a weather alert system and a operational protocol with a clear chain of command to move the panels to safe stow angles. You should choose trackers that have a quick response to the approaching storm, and you should choose trackers and modules that safely ride out the impacts associated with that storm. Finally, we wanted to point out that the investor is interested in risk in a given year and relate that to the protection from whatever insurance is in place. But they're also interested in exposure over longer periods of time, where, in particular where the hold period for the investment is greater than the return interval. So, investors should be concerned with the finite possibility of more than one event during the hold period. VDE has developed a tool based on Poisson distribution that, knowing the return interval for different hail sizes, we can estimate the likely number of events and associated average annual losses as a function of hail size. And with that, I'd like to thank you for your attention and look forward to your questions in the Q&A session later on. Thank you.